Today I'll be talking about galaxies, obviously, and what I use blue waters for is to simulate these galaxies, because that's the main way we have of approaching the problem. And when I say galaxies, here we have a mock image of one of the simulations, and I'm not thinking about this nice spiral galaxy in the middle. I'm not even necessarily only talking about these, but I'm also studying the galaxies, which to you might just look like a smudge on the screen over here. But first, let's take a step back and go through some background. So in the field of galaxy formation, particularly as relates to smaller galaxies, there are a lot of open questions. In particular, some of them are, how big are the smallest galaxies, and even is there a smallest galaxy? How many nearby galaxies are there? We don't have a complete census near the Milky Way, and as you go further out, it becomes more incomplete. And so one of the questions we're seeking to answer with simulations is, how many are there? And as well, how do stars form in galaxies? So what are the local conditions for gas that are necessary for the gas to collapse and turn into stars? And then there are many more questions. The list goes on. Why do galaxies stop forming stars? This is mass dependent, et cetera, et cetera. What I'll be focusing on in this talk are primarily these two questions. How many galaxies are there, and what determines how many galaxies there are, and then how do stars form in galaxies? And as a corollary to this, I'll be kind of flipping the question around and saying, from our simulations, what conclusions can we safely draw about these questions? So the current understanding of galaxy formation is summarized here. No need to learn anymore. This is it. Just kidding. In our current understanding, most matter, about 85% of it, is dark matter. We don't necessarily know what it is, but we know pretty well how it behaves from a variety of observations. And so this dark matter behaves only under the influence of gravity. It's collisionless, and we're able to put it in our simulations. The at the beginning of time, initial density perturbations are seeded, and these perturbations grow with time under the influence of gravity. And over time, dark matter falls into these potential wells, grows, and forms what we call dark matter halos, which are these overdense clumps of dark matter. And it's within these dark matter halos that gas flows, and through processes I'll describe in more detail later, forms the first stars and the first galaxies. And over time, these many different dark matter halos and galaxies can gain mass and merge, and you end up with something that looks like the bottom circle here, where if that's the Milky Way in the middle, the luminous counterpart, you have a much larger dark matter halo within which it resides, not to scale here, and many subhalos that exist within this that would be the satellites. And importantly, not all of them necessarily contain stars. Some of these might just be dark matter halos. And so another way you could phrase this question is not just what determines the first stars, but how do you put stars into these dark matter halos to make galaxies? So for a long time, the way to approach this question, please work, yes. The way to approach this question was with simulations of just dark matter. This is taken from the Via Lactea simulation, and that bright spot in the middle that you see would be analogous to the Milky Way. But, and as you can see, it's very complicated, and over time, many of these halos and subhalos merge. But of course, this leaves the open question of how you connect the luminous counterparts, the galaxies, to the dark matter that we see. And to answer this question more fully, we need to run hydrodynamic simulations. And so that's what I focus on. Here we see one of the simulations that will eventually turn to be like a galaxy like the Milky Way, as you'll see in a minute or so. And so what these simulations do is they start from initial conditions that we can infer from observations, and you simulate dark matter only under the influence of gravity, and gas, which is primarily hydrogen and helium initially, under the influence of gravity and hydrodynamics, and eventually these stars form from the gas. And as you can see, it's very complicated. Here the purple is stars, I believe, and then the kind of greenish white is gas. And in these modern simulations, however, this isn't enough. We also, because of resolution limits, we have to put in what we call a sub-resolution, or if you're a grid code, subgrid recipes, which are analytic descriptions of things that happen below our resolution scale. So the way that gas turns into stars is actually one of these subgrid codes. We also include things like feedback, which would be the energy return from primarily massive stars into surrounding gas, and so on. And using this combination of physics, we and many different modern cosmological simulations are able to reproduce realistic galaxies, such as the one you see here. Of course, most modern simulations have different origins. So we're using different codes with different sub-resolution physics, and we all manage to produce realistic galaxies. So the question is, what can we do to constrain what's going on beneath the surface? And this ties in, the reason for this convergence is largely due to something called galaxy self-regulation. So when you're in a regime with a sufficiently large gravitational potential well and sufficiently strong feedback, the opposing processes of star formation and feedback regulate themselves. So here on the left, for example, you see the total star formation rate as a function of time. And this is for 3 different density thresholds. So once the gas reaches each of these densities, it has a probability of forming stars. And what you see is that despite an order of magnitude variation in this density threshold, the star formation rate remains exactly the same. And kind of an intuitive understanding for this would be, if you make it easier to form stars, then more stars will form initially, but the massive stars, the feedback from the massive stars will then lead to more energetic feedback, which prevents further star formation. And so these opposing processes lead to these global properties that remain converged. So if we want to understand how does gas form into stars, we need to enter a regime where galaxies cannot self-regulate. And this regime requires a lower star formation rate and less feedback, and smaller gravitational potential wells. So we have to enter the regime of dwarf galaxies and the faintest yet known galaxies, ultra-faint dwarf galaxies. So what are these things? Well, here we see, this is real, not a simulation. This is probably what most people think of when they think of a galaxy. This is what we call a grand design spiral. It's got this beautiful, clear structure, possibly a bar in the middle, dust lanes, et cetera, et cetera. When I think of a galaxy, I think of something more like this. It may not look like much, and in fact, the brightest stars aren't even in the galaxy. They're foreground stars from the Milky Way. But these overdense clumps in the middle that you see are actually galaxies, and they reside in their own very small, relatively speaking, dark matter halos. And if we can simulate galaxies that are analogs to this, then we can start to answer the question, how does gas form into stars, and does it make a difference if we change the underlying mechanism? So just to recap, we want to study very small galaxies in large enough numbers where we can actually draw conclusions from the differences. And we want this in a fully cosmological context where you have gas inflow and outflow and large-scale torques and things like that. So for this, we need very high-resolution cosmological hydrodynamic simulations. And this is, of course, where blue waters comes in. Oh, the challenge here, which in some ways is unique to cosmological simulations, is an issue of scale. We have enormous dynamic ranges, both in time and space. Just to give an idea, in the highest resolution simulations, the entire box might be more than 100 million light years across, but in the high resolution region, which would be in the center, the part of interest, the hydrodynamics and gravity might be on the order of tens or hundreds of light years. In terms of time, we're simulating the age of the universe, so about 13.8 billion years, yet for high velocity, high sound speed gas, we might go down to hundreds or thousands of years for the force calculations. So this enormous dynamic range requires special computers in order to actually meet the demands in terms of computation, communication, and memory. And then just as a reminder, despite the fact that we have this huge range, these processes that we're modeling occur well below even the resolution we can resolve here. So star formation occurs below these tens of light year scales, and this is why we have to put them in as subgrid recipes or sub-resolution recipes. And then another challenge, or the way we have of handling these massive simulations is with specialized codes. Now, some of you, depending on the talks you've attended, might have already heard a little bit about Changa. I won't go into too much detail, but this is a smooth particle hydrodynamics code, and it includes all of the modern SPH fixes and the physics modules of the earlier gasoline code. And what makes it particularly well adapted for these kinds of simulations is that it uses the Charm++ runtime system, which allows for things like dynamic load balancing, which are very important when you have these simulations that become very spatially clustered and could lead to enormous imbalances in terms of computation requirements. And this allows scalability on massively parallel systems like blue waters. This shows the dark matter density. And as you can see, as you approach the present day, it becomes very inhomogeneous. And just as a precursor for what we'll be looking at next, the Milky Way would be at something like one of these nodes in the web, and a more isolated region might be in a less bright region of one of these webs. So back to the question at hand, we want to constrain star formation using cosmological simulations. To do this, we focus on two star formation models. The first one we've dubbed metal cooling, and it basically works with a density threshold. This is pretty similar to the way most cosmological simulations implement star formation. Once the gas is dense enough, it has some probability of collapsing into stars. The other star formation model we use is the H2, or molecular hydrogen model. And this one is actually based on tracking the non-equilibrium abundance of molecular hydrogen within the gas. And it requires a sufficiently high abundance of H2 in order to form stars. And the effect this tends to have, at least in gas that doesn't have a lot of heavier elements, is that it requires higher densities to form stars and longer time scales to actually build up the abundance of molecular hydrogen. So with these two star formation models, we also want this to be a more comprehensive comparison. So we compare across multiple environments. The first environment that we compare to is one of these isolated environments. This would be something 15 million light years from the Milky Way with no massive galaxies in the area. These also happen to be easier to simulate. And so I'll come back to that. And then the other environment we're looking at is analogous to the Milky Way. So one of the special aspects of this work is that in order to resolve these very small galaxies, you need incredibly high resolution. And when you're simulating the Milky Way, that becomes very difficult. So this is what we've done. The numbers are up there for those interested, but the gist of it is that the resolution is high enough to actually resolve these very small galaxies. And at least of simulations that have been run to the present day, these constitute, I believe, the highest mass resolution of any Milky Way analogs that have been run. Though there are others that haven't been run to the present day yet that are comparable. And so with these comparisons in hand, let's see what we actually find. This is a typical plot that we use in astronomy. This shows the relationship between the stellar mass of a galaxy on the y-axis and the mass of the halo on the x-axis. And then each point here represents a galaxy. On the left, we have the metal cooling run, and on the right, we have molecular hydrogen. And what you can see immediately is that there are fewer points in the H2 run than there are in the metal cooling run. And if you look more closely, the stars represent satellites, whereas the circles represent galaxies that are not satellite, or halos that are not satellites of another. And what you can see is this difference primarily affects lower masses, which happen to be mostly satellites. So there's a factor of 2 reduction in the number of galaxies when using the H2 run, but it's a factor of 5 among only satellites. So this is obviously an enormous difference. And the reason for this is that, as I mentioned earlier, if you're requiring H2 to form stars, you in unenriched gas, which is the gas you have in the first star, or when you're forming the first stars, it requires much longer timescales to actually begin forming stars. Thank you. And we don't really have the entire length of the age of the universe to form these stars because something called reionization, which is just this cosmic background of ionizing radiation, ultimately kicks in and suppresses further star formation in very small galaxies. So in a bit of a race against time, this suppresses star formation, or delays star formation long enough such that it completely prevents it from ever beginning at all. And if this is one way to see this. If we then more or less bin it up according to halo mass, you can look at it this way, and the differences become even clearer. In larger halos, greater than about 10 to the 9 times the mass of our sun, you end up with the exact same number of galaxies, and they have some pretty similar properties between the two star formation models. And this is consistent with what we know about galaxy self-regulation, where when you're in these regimes of greater feedback and larger potential wells, you should expect converged results. But it's below this mass scale where the difference becomes quite large. So these are in results in regions far from the Milky Way, where you only have dwarf galaxies. You have no massive galaxy like the Milky Way to influence the galaxies or to tell you anything about the cosmological environment that you find yourself in. When you're simulating near the Milky Way, though, we end up with, surprisingly, very different results. So what I want to draw your eye to are the thick green lines and thick blue dashed lines. The blue dotted line is a function of the way I had to run the simulations and do the matching procedure. I don't have time to talk about it, but I'm happy to answer any questions you may have. But when you're looking at the H2 versus metal cooling run, you notice that whereas before, below about 10 to the 9 in halo mass, you formed far more galaxies with metal cooling run, here they're essentially the same. There are no significant differences between the number of galaxies that form. And it turns out the reason for this is all about the environment. The cosmological regions where massive galaxies like the Milky Way reside are these overdense regions. And this larger background density allows the gas in these halos, even the smaller ones, to reach higher densities and reduce the timescale for the formation of H2 as compared to the isolated environment. And because they can form stars faster, they are actually able to form galaxies before the onset of reionization. There are also some secondary effects from environment where the pre-enrichment, the pollution of heavier elements from the most massive galaxy allows some of these galaxies to form with gas that is pristine, and that also drastically reduces the time scale for the formation of molecular hydrogen. So what this tells us is that from the differences we see in the isolated regions, first of all, cosmological simulations can be used as a very powerful tool to constrain even small-scale physics that would be considered very local compared to the entire cosmological region. However, environment matters. And this should serve as a cautionary reminder to simulators, because oftentimes, due to the greater ease of simulating these isolated regions, we like to draw conclusions from those regions and say, okay, in a Milky Way environment, it might end up looking like this. And this serves as a cautionary reminder that results might differ environment to environment, and we can't assume that our results are going to be broadly true in all cases. So with that, because I see you standing up, I'm going to leave up my summary and also say a quick thank you to my point of contact, Robert Brunner, to Scott Lathrop, and to the entire Blue Waters team for their assistance and support during this fellowship. It's been a wonderful experience, and I hope to keep working on the Blue Water system in the future. Thank you.